Well, if you've had stats, you should recognize this is equation for your standard normal curve. We're going to go ahead and find our inflection points on a standard normal curve. Well, we're going to go ahead and first of all take your derivative. Well, you should remember for your derivative of an e to the power, it's that times the derivative of the exponents. So we just have this in front. Here it's e to that power. Derivative of your exponent is just a negative x, because it's really a negative 1/2 x, but then multiplied by a 2. That 2 undoes the 1/2, so it's just negative x. Well, if you wanted, you could just take that negative and put it here. So now the inflection point, once again, you got to do second derivative. So I'm going to just leave that fraction in front. And then just go ahead and do the product rule, because we're multiplying variables together, because it's a negative x times this. So it's product rule. Derivative of the first. Oh, sorry. I switched it around on this one. I did the derivative of the second times the first. So here's your first. This part right here is just the derivative of the second part. Plus derivative of the first multiplied by the second. Well, that's going to simplify a little bit. You'll notice you'll get an x squared here. You'll get a minus a 1 here. Leave that in front. Now, you might be wondering, what did I do? Well, all I did was just go ahead and pull out my common factor here. Common factor of this and this comes out to be this here. Leaves me only with my x times x, or x squared, and plus a negative 1, which is minus 1. Now we have to set our derivative equal to 0, our second derivative. And we want to go ahead and do that. We set this equal to 0 and solve it. Well, this is just a number in front. You never have to be concerned about that being 0. This is e to a power. You never have to be concerned about that being 0. Then when is x squared minus 1 equal to 0? Well, that's at plus or minus 1. Well, it's really neat that your inflection points on your standard normal curve occur at a z-score of 1 unit to the right and a z-score of 1 unit to the left. Now, sometimes in your stats class, you're asked to approximate your standard deviation, and it was always from when it switched to concave down to concave up. That's called your points of inflection. So now we need to go ahead and solve these. We need to integrate. Well, the derivative of e to the u is e to the u. So when you integrate e to the u, you get e to the u plus a c. So we're going to go ahead and do that here. We're going to let u be our negative x squared. So therefore, our du is a negative 2x. Or we get dx to be this. So for our problem, we have this. Remember, you can always pull that constant in front, which is the 5. And then you're going to have an e to the u, because remember, negative x squared is your u. Your dx gets replaced with this here. The 5, the negative of the 2 come in front as constants. So then you just have the integral of e to the u. Remember, when you integrate e to a power, just like the derivative, it's e to that power. But then since it's indefinite, you got to go plus c. And so then you want to substitute in what u is. And so you get negative 5/2 e to the negative x squared plus c. So yes, you're going to sometimes want to use u substitution. Some of you might be able to do some of these problems without the u, but if you need to, go ahead and do the u. Looking at this one here, you may want to go ahead and rewrite the first one here, your integral, as an e to the 1 over x times a 1 over an x squared dx. That may make it easier for you to identify what u is. In this case, we're going to let u represent the higher exponent, because this is an x to the negative 1, that's an x to the negative 2. So therefore, du is this. Oh, well, we can work with that, because this stuff here shows up in our problem. So we're going to write this. We're going to write that. Here's our du that we have right here. But we're going to have a negative here to offset that. So then all we're going to do is integrate, because for the most part, it's an e to the u integral with a negative here, du is really what it boils down to. When you integrate that, that's what you get. Because you would get an e to the u plus c, your u is this. When we look over here, we have several things multiplied together. We have a sine times an e to a power. Well, if we let u represent what your exponent is, then du would be this. Then it's pretty easy to go ahead and work out. So we get our e to the u here. We get our du over here. But notice, to keep this the same, we've got to have a negative in front to offset that negative. So now it's really in the form of a negative integral e to the u du, which you should know is in negative e to the u plus a c. Then you want to substitute in what your u is to get your answer. U was your cosine of x. So let's go ahead and integrate this definite integral and evaluate it. You have a couple options here. You could let u be the top, or you could let u be the bottom. But if u was the top, the derivative of that's e to the x, and we don't have that 1 shown up. If you let u be the bottom, we get this, and the derivative of that is e to the dx. And you notice this right here shows up right here. So the highlighted stuff there is really just a du. So for our particular problem, we really have the integral of a 1 over our u with a du afterwards. Since it's a definite integral, though, we should go ahead and change our limits, because we went from an x's for our limits to u's. And so when you take 0 and plug it in here, e to the 0 is 1, so 1 plus 1 is 2. Plug it in your upper limit of 1, you get an e plus a 1, or 1 plus e. So now when you integrate this, you know 1 over u goes to the natural log of u. Then you need to evaluate that from 2 to your 1 plus e. So you want to go ahead, plug in your natural log of your upper limit, 1 plus e, minus what you get when you plug in your lower limit, which is a 2. Now, if you chose to use u substitution, that's how you would work it out. Could you go ahead and rewrite this in terms of x's again here, but no need to. If you did rewrite it in terms of x's, you would get this. Some of you may have been able to go straight from this original to this problem here because you saw how to have it integrated just in your head. Then you'd have to plug in your 1, plug in your 0, and gee, you get the same answer. Doesn't make a difference. Now, you could also do a decimal approximation. But don't just give me the decimal approximation. I'll need the exact answer unless it specifies to approximate.